Okay, so before we start this, our second lecture, can I ask everyone to have a look at, if you haven't done this already, have a look at the web page. The program at the bottom of that page, there is the program description and all the reading that everyone has done before coming here. But at the end of that page, there are instructions for installing the software needed for the tutorials in the afternoon. If you haven't done this, please make sure that by the end of the lunch break, this is all done and in place. There is option 1, which will be used in the second tutorial for local software installation, and option 2 for using Google Colab. It will be used in the first tutorial. Also, this is the program section. In the materials section, there's already some information about today's tutorials. So there are some files and some links that you will need to access for the tutorials. All right, so our second lecturer is Steve Abel, the professor of theoretical physics at Durham University, and he's going to instruct us about genetic algorithms. Thank you, Steve.
Right, okay. Oops. Oh, there we go. Is that better? So, so the title of my talk is, my course is, so it's Heuristics for Physics is what I call it. Is that too loud? Okay. Is that better? All right, so shout if you can't hear me, basically. So I was given the task of talking about meta-heuristics in physics. Can I do this? Yeah. Meta-heuristics. So I gave the title heuristics. And so just for a bit of semantics, the difference between heuristics and meta-heuristics is that meta-heuristics is something which is supposed to be more elevated than heuristic. Heuristics is things similar to kind of gradient descent or Nelder-Mead method or something like that, where you're searching a parameter space. Meta-heuristics, as I'll get into in a minute, is more to do with taking some sort of very convoluted picture, and I've actually put maybe neural networks in that category actually, and thinking of a way to solve a problem in a much more refined way. So this is the way I've arranged things. I'm going to spend today talking about, well, introducing the notion of what some meta-heuristics, where we are, what sort of techniques they include. And then today I'll talk about genetic algorithms, which is one particular meta-heuristic method. And then there'll be a tutorial, which is going to be led by Thomas over there. And then tomorrow I'll talk about annealing, essentially. And so a particular type of annealing, quantum annealing. So it's a sort of version of quantum computing, which has become more popular recently, quantum annealing. And the benefit of that is it will also tell you something about simulated annealing, which is a different sort of annealing. And then also adiabatic quantum computing is a kind of relative of quantum annealing. So I'll also tell you what that means. And then the tutor tomorrow will be Luca, who's sitting in the audience there. So that's Luca. Okay. And then the third lecture, I'm going to talk about some of the applications we've been doing. And so it's going to be, that's more kind of oriented about the stuff we've been doing, because it's what I know about, essentially. But it's, and so I'll give you something which is a bit more sort of current. Right, so this lecture, what I'm going to do, I'm going to talk about meta-heuristics, first of all. And then I'll give you the background about genetic algorithms, so what genetic algorithms are and why they work. And I'm going to be focusing on string theory in this talk. So string landscapes is going to be my motivation, essentially. And then I'll give you some ideas about why they work. Then sort of in common to some of the aspects of neural networks, it's not really understood why they work so well, but they do work very well. It's a kind of, it's almost an experimental science, the heuristics, meta-heuristics. And then I'll talk about a toy problem. And the one I'm going to talk about is just finding taxi cab numbers, which is a particular number theoretical problem. And then I'll sort of talk about ways that you could adapt genetic algorithms in more convoluted ways, so coupling them with other search techniques. And I think there's still more work to be done, and I think there are still possibilities for developing new techniques that include genetic algorithms in combination with other things. So I'll talk about those. Right, so here's the motivation for me, which is the kind of stringy motivation. Essentially, that's where I started with this, which is that as you are probably or maybe aware, in string theory, very often you end up with a set of parameters that describe the model. And so you may have several parameters, typically not a huge number of parameters, but it can define an extremely large number of models. And the trick is, how do I find the right model amongst the huge parameter space that I have to look at? And so you're left with some problem to solve. For example, a phenomenological problem such as, how do I get 3 generations, for example, in my particular model? How do I cancel anomalies and various other consistency conditions, which in string theory would be GSO constraints, for example, those sorts of conditions. And you have to solve those things, and typically it's very hard to find a solution, or it's not so easy to find a solution. And you don't really know how many of these solutions there are in the search space. So it's something which you would say is computationally hard. Which I will take to mean that if I increase my parameter space, if I have 20 parameters, it's an awful lot harder than if I only have 10 parameters. So the search space increases possibly exponentially even. So some of the techniques that have been used for that are machine learning, for example, and neural networks. So it's a big data problem, and one of the methods which has been less looked at in this context, really, genetic algorithms. So that's where I came in, genetic algorithms. So this is it's an old technique, genetic algorithms. It was invented, thought of, I think Turing was the first one to mention it, and it was further developed a little bit by these guys, but then the person that really nailed the subject was John Holland, which was still a long time ago. That was in the 60s, I think, or early 70s maybe. And then from then on, it sort of it had more successful applications since then, but it really sort of took off after, I'd say, the turn of the century. So in the 2000s, people really started to consider this as a useful technique. Right, okay, so that's the motivation. So now let me just tell you a bit more about meta-heuristics and the sorts of problems that we are looking at and what meta-heuristics means. So meta-heuristics, I would say, is any kind of subject, any kind of technique where you're trying to find a solution which takes its structure from things that happen in nature in some form or other. So if you think about what happens in nature, so for example, finding a hemoglobin molecule, for example, or constructing antibodies and so on, all of these things, if you think about what's available, it's almost impossible to come up with a solution yourself, and yet nature does it all the time. So it looks as if, so sometimes these things are used as proof of the existence of God. For example, hemoglobin comes up quite a lot. Those solutions are so extraordinary that, surely there's something we can learn from those. So that's really where genetic algorithm comes in, and all of these meta-heuristic techniques. And so let me just sort of tell you where they kind of sit on the computational complexity diagram. So So this is roughly explaining to you, the P and the NP categories of computational complexity. So if we assume that P is not NP, then problems which you would say are easy are those which are in P. So those are kind of boring problems, I would say, and boring games. So noughts and crosses, for example, is something in P where you can just solve it by exhausting the possibilities. And if I give you a larger noughts and crosses, you probably can do it in something which increases polynomially with the size. Other games sort of appear over here. So in NP, so NP is where if you have an extraordinary amount of luck, an infinite amount of luck available to you, you can solve it as fast as you can a problem in P. And so typically you're thinking in terms of decision problems. And to decide if you're going to get a yes or a no. And there's usually in NP an idea that you're solving a problem by making a decision at some point, and you always make the right decision. So that's one way to think about it. Another way to think about it, which is usually people say, is that problem NP is something where you can check the solution in polynomial time. So NP are things like graph isomorphism, and then there's what are called NP hard, which are problems which are harder than NP, and NP complete are on the borderline between NP and P. And so the kind of peculiar thing for us anyway is that one problem which is NP complete is what's called genome assembly. And so that is when you're trying to analyze DNA, for example, you quite often measure, you just know short sequences, you get short sequences, and you have to reconstruct the entire genome in some, and so you have to order them in the correct way. And so that's called genome assembly. That's known to be NP complete, and genome assembly, but also so are many stringy sorts of constructions. So they're kind of some similarity that you can reduce one to the other. And then other games like Tetris and Knapsack are NP complete. And then chess is what's called X complete. X is something which increases as an exponential of a polynomial of the size. And then there are problems here. Halting problem is undecidable, it's called. Anyway, so we're typically thinking about problems which are kind of here, which are NP complete. Certainly when we're thinking about string theory. So this is the sorts of techniques that you're commonly may use if you're going to do meta-heuristics to try and solve it. So this is taken from Wiki, this diagram. And so a meta-heuristics is this big gray box here. Some of the techniques I'll look at, so tomorrow we'll be doing annealing, we'll be doing quantum annealing. So here's simulated annealing, which is copying a kind of something that happens in nature when you're sort of freezing something or reducing the temperature, and it's kind of crystallizing a system. So simulated annealing is sort of copying that process. We're interested in doing the things down here, which are based on nature. So that's kind of copying things that go on in nature. The things I'll talk about tomorrow, so quantum annealing and adiabatic quantum computing. It's not so obvious where those go on this diagram. Quantum annealing is something you could say, okay, it kind of happens in nature, because if you assume that there's phase transitions in the early universe, for example, it's kind of copying that process. So quantum annealing is sort of copying something from nature. Adiabatic quantum computing, not so much. So I don't think, so adiabatic quantum computing, which is also true in quantum annealing, you're sort of changing the Hamiltonian of the system. And it's not so, I can't really think of a situation in nature really where that happens, where you're changing a Hamiltonian. So it's not really clear where those go on this diagram, actually. Right, okay, but we're going to be today talking about those ones. So genetic algorithms, genetic programming, and evolutionary programming, and so on. But we're mainly talking about genetic algorithms in this lecture. Genetic programming is related to genetic algorithms. They're all basically copying evolution, so some strategy from evolution. Okay, so that's the meta-heuristics overview. And now let me get on to genetic algorithms. Yeah. NP. So NP complete are supposed to be the hardest problems in NP. And so you show it by reducing those problems to a problem you already know to be NP complete. So, yeah. No, I mean, it's, yeah, so it's not that you can't check all the possibilities because they increase too fast. So it's not like, you want to avoid having to check all the possibilities. Yeah, so the number of solutions grows can be kind of exponential growth, for example, the number of solutions, given the size, the growth in the size of the problem. Yeah. So we want to try and avoid, that's the thing, you don't have the time to check all of the possible solutions. So you want to find a different way to do it. So let me just go back to the motivation from nature. And I'm just going to look at this. So this is a hemoglobin molecule. I'm going to just imagine that I'm approaching this as a physicist. So I want to decide how difficult would it be for me as a physicist to invent a molecule which can carry oxygen. So this is like this is a hemoglobin molecule. And it's constructed like that. So it's got nearly 3,000 carbon atoms in it, and it's got nearly 5,000 hydrogen, and so on. So you have to imagine, all I'm given is this set of molecules. I have to construct them in a certain way in order to make a molecule, a set of atoms. I have to put them together in a way which will allow me to carry oxygen. And you'll see, actually, hemoglobin already has 800 oxygen molecules in it. So not only I'm using this to carry oxygen, I have to find 800 oxygen atoms to make just one molecule. So it has to do 800 circuits before you even benefit from this thing, right? So I have to find 800 oxygen atoms to put in here, and it can carry 4 atoms of oxygen. So I guess it's 200 circuits before I actually start to benefit. Anyway, so if I just approach it, if I just estimate how difficult is it for me to find that solution, I could, for example, think of taking carbon, hydrogen, and iron, and so on. I've got 92 elements to choose. And so I get that sort of number of possible attempts in order to find a solution. I could alternatively try and estimate it this way by, first of all, I have amino acids, and I've got 141 of them. And I count the number of amino acids in this thing, and then I multiply it that way. So then it's only 10 to the 747. Alternatively, you can think, okay, well, first of all, I have to make a human, and so the chances of that is 4 to the 3 billion or so. So you see, these numbers that you get, and sometimes you see these numbers quoted in string theory literature, are sort of meaningless because it depends entirely how the thing is put together. If I decide to try and just throw down atoms, I would have to be extremely lucky to get a hemoglobin molecule out of it, but that's not how it's put together. So that's the point, is in order to solve this problem, we don't approach it by just doing a search. So that's our inspiration. Right, so genetic algorithms can solve that kind of problem. And so it's based on evolutionary dynamics, and they work effectively when, if you're thinking about many criteria that you're trying to solve at the same time, so you have many requirements, and also, so there was some work on this in the 1990s, early 2000s, about why they actually work. And there's a thought that there's a large parameter space, and you're thinking about a fitness in the parameter space, and you need in the parameter space a correlation between a goodness of fit and how close you are to the maximum in some sense. So it's a kind of gradient descent, if you like, that you're doing, but the parameter space could be extremely complicated. It doesn't have to be continuous. and so on. But there's an idea that in this parameter space, you sort of think of it as a kind of Hamming space or something. It's just a sort of code space. There has to be some sort of correlation between making small adjustments and getting closer to the solution. So that was, there's some idea that that's behind why they work. The disadvantage is that they're, by their nature, it's very hard to get statistical information. So if you want to know how many hemoglobin molecules are there possible, it's very difficult for me to tell you because I can't search all of the possible hemoglobin space. And so I can't tell you, there are, I think there's something like 4 or so different types of hemoglobin molecules. I can't tell you if there are maybe hundreds, I don't know. Right, so let me just sort of start to show you how it works, a genetic algorithm. So I'm going to give you this problem. It's a continuous problem, but I want you to bear in mind that genetic algorithms don't work. They don't have to be continuous problems. They can be discrete problems, and that's actually where they excel, really. But anyway, just for demonstration, I'm going to show you this continuous one. And it's to find the maximum of some function. So I'll give you a function, and I want to know the global maximum of this function. And so it's got lots of local maxima, but I want to know which is the highest one. And so this is how you can do it as a genetic algorithm. What I'm going to do is I'm going to consider like an attempt at finding. I'm just going to take a random x and random y. And I'm going to consider that to be an attempt. And I'm going to do it to 250 decimal places. And so if you think about the numbers here, so I've got A dot B, C, D, E, F, and Y is G dot H, I, J, K. So I've got, this is 10 to the 500 if I want 250 decimal places. So it's a kind of string theory sized problem, if you like, if I don't know about calculus. Right, so now what I'm going to do is I'm going to define a random attempt as a creature. So I'm going to think of it as a creature. And this creature, it's defined by its x and y values. So my guess, my random guess, my x and y guess, I'm going to call that the genome. And so the genotype is how you refer to it, actually, the data in the thing. So that's A, B, C, D, E, F, and G, H, I, J, K, L. So all of those numbers, I just think of it as just data. But this data gives rise to a phenotype. And in this particular example, the phenotype is so that's the physical characteristics that come from the genotype. The phenotype in this case is just the function. But it could be anything. So it's whatever I'm interested in, that's the phenotype. So it's whatever the data gives me, that's the phenotype of my creature. So that's the biological language that we're using. So a single creature will just be occupying a point on this, and it will have a certain fitness, which I'll talk about in a minute. But it'll be higher or lower, and the higher it is, obviously, it's better if it's higher. It's not so good if it's lower. And so I'm going to define a fitness function. So I take a population of 100 of these things, and I sprinkle them at random over the surface, and I calculate for each one its function, so the phenotype, the f of x, y. And from the function, I define a fitness. And so it could just be the function itself, if I'm looking at the maximum, or it could be something much more complicated. And we'll get on to a specific example later, but it's really up to me to decide how I define the fitness. So I may decide, well, I'm going to do it as f squared or something, or quite often, and what I'm going to tell you later, is that I simply rank the creatures. So the best creature is going to get the rank 1, and the worst is going to be rank 100, and the fitness, I'm just going to calculate it from the rank. So it could just be, F, it could be 100 minus that. So the best is fitness 99, the worst is fitness 1. Right, so the next step is then selection. So what I'm going to do is I take my population, and I'm going to select them for breeding. And the breeding, I'm going to take, in this particular example, pairs. So I'm going to take from the population. I'm going to select pairs, and the probability of selection for breeding depends on the fitness. So I select for breeding. Of course, the fitter creatures I select for breeding more often than the unfit ones. And typically, you would have a ratio, something like 2 or 3 or so, that the fittest creature gets to breed 2 or 3 times more often than the least fit, something like that. And so the way that I'm doing it, if I just do it by the way that I've ranked them, if they have a ranking K, then I can assign a probability that it's going to breed, which is this formula. So alpha you can think of as the learning rate, and you can see if K is equal to, if K is n pop, then this is just 1 times by the prefactor, and if K is equal to 1, it's alpha times the prefactor, so that the best creature gets to breed alpha times more often than the poor least best creature or worst creature. Right, so then that's selection, and now we do breeding, and the breeding is, what I do is I take so I completely ignore the phenotype. I just look at the data which defines the creature, so that's the genotype, and I do some operation on a pair, on a breeding pair. So for example, the simplest is a single point crossover, so that I'll just take the genotype and I splice it, I cut it halfway or some random point along the same point on each creature, and I swap the tails, the genotype, and then I get 2 new creatures from that. And I do that across the whole population, so I do it for n pop times, and I have a new population which has come out of the old population. So that's breeding. And finally, there's a step which is very important in this process, which is mutation. So when I have my new population now, I need to just randomly flip some of the bits of data. So the bits of data are called alleles, by the way. So I'm going to randomly just joggle the thing a little bit, and I'm going to change the data a certain amount. And the proportion is something like maybe 1% or something like that. Typically 1%, 2%, something like that, of the alleles get changed, get flipped. So that's mutation. And it is important, this particular step. It looks kind of like, is this just like randomly copying what happens in nature for no particular reason? Mutation is actually an extremely important step. If you don't do mutation, it does not work. It doesn't work. Right, so now what we do is we repeat that. So we breed over a lot of generations, and what happens is that the population converges around solutions. So I'm going to show you for this particular example. So this is just plotting the population. Yep.
Can you say something? I mean, I kind of get it from. Can you say something about? Can you say something about why mutation is so important? So you might think that if you started with a big enough data set, you had the right numbers to get the maximum in each of the decimal places, and you just had to swap.
Yeah. So what happens? Actually, if I just do this, I just do this a few times. Yeah. So after a few generations, you get that sort of arrangement. So now, if I don't have mutation, what can happen is that the population is just stuck around one maximum, which may not be the best one. So it might just be there. And that population is kind of entirely, at that point, it's become entirely sterile because it's no longer exploring the whole landscape. It's really just everyone's focused around that one point. And without mutation, it never goes to explore somewhere else. So what mutation does, I'll say a bit more about it in a minute, but it sort of pushes you away from the attractive part. So you don't get stuck in local minima of potential, if you like. That's sort of my, that's at least one reason why it's necessary, but it's actually, it seems to be even more important than that, that they don't even focus very well without mutation. So, when they're starting initially, if I sprinkle them over the whole landscape, they can kind of they're all sort of useless apart from maybe one lucky one. And so it just becomes a very sterile process. They don't really start to converge very well, actually. Right, okay, so this is how they converge, and you get something that looks like that in the end. And so you get from that, you get very close to the optimum. You get very close to the optimum. You don't get exactly there. And what happens is, and I'll talk a bit more about it, is the convergence starts to slow down when everyone's sitting around the best point. And so there are ways to try and get around that slow convergence, but we'll get back to that. Anyway, the good point about it is it's very independent of things like local attractive points, local minima in the fitness landscape. So here's something, it's a much more complicated potential, which has got like an awful lot of minima. If I was doing something like a gradient descent, I would have a great deal of difficulty in this landscape finding the best maximum, because I can almost can't avoid hitting a local maximum, right? So I can't avoid it. What happens with this is that there's no kind of dynamical, there's no dynamical idea that the individuals are moving across the landscape or anything. Every time you breed a new generation, it's completely sort of wiped out the old generation. It's just constructed an entirely new generation from the genotypes. And so it's not moving dynamically. It doesn't know that there are maximum points in the way, if you like. So it will really just start to line up. Even if the landscape is very complicated, it starts to find the right point. So in a way, it's sampling the whole landscape as you're doing this. So let me just show you this flowchart. I'll get back to this. Flowchart later, probably in lecture 3, probably. But this is a way to represent it. And if you've seen, for example, reinforcement learning topology flowcharts for that, it's a similar sort of flowchart to reinforcement learning. So, and so what happens is you have a set of genotypes, so that's data. You split them up into breeding pairs, you do some crossover, you get a new population, do some mutation, you get a new set of genotypes. Yep.
Then if you reverse the steps of mutation and crossover, if you do like mutation first,
do you know what
would you expect in terms of the result?
That's a good question. I mean, I think essentially it's because it's circular. I don't think there's really an ordering. Yeah, you're doing the crossover, and then, so I guess you could say, do I do mutation after selection, or it doesn't really matter. Yeah, it's the same. Yeah.
How important is your choice of crossover function?
So it's so you can do, for example, 2-point crossover and various different combinations. In the end, it doesn't make a difference. From my own experience, people have promoted sort of, for example, 2-point crossover because you could get sort of edge effects. And if I'm only crossing over at 1 point and maybe perhaps one of the end alleles is very important, then I may be better off doing a 2-point crossover. But just in my own experience, I've never had any problem like that. So 1-point crossover is fine, but you can do 2-point crossover. Yeah.
Yeah, I have another question regarding the selection. Is it only that you select the pairs for breeding and throw away all non-fit points, like they are die out, or do you still keep them? Because in your chart, it looked like you neglect at a certain point some points in the landscape.
So sorry, what was the question again? Do I throw away?
In the selection part, do you keep all points, or do you throw away points?
I mean, it's the creatures. I mean, forget the points. The creatures are the things which I'm selecting or not.
Yes. Yeah.
And you can do it different ways. So I'll kind of get onto that a little bit later. There's something where it's called a steady state, where what you do is you replace some of the population, but you keep a lot of the population. Yeah, so I'll get onto these sort of tweaks a bit later.
Yeah, so the essential question was whether the population grows monotonically,
right, okay.
or whether you keep a certain number of individuals.
Typically you would keep the same size population.
Yeah, like from a numerical viewpoint, like storing the data, I would think of.
Right, yeah, so for storing the data, the way that I normally do it, if I'm doing like a ranking, sorry, I have to do that. Okay. If I'm just ranking it, what I do in practice is I just have like an array, and I will put the genotypes in an array, and I would just like physically change the position in the array. And the benefit of doing that is that when I'm calculating the probability for selection, I can just have one like a vector, you know, it's just something where I act on the array.
I see, yeah.
And so wherever they are in the array, it determines how much I'm going to choose them or not. So it's easier to do that, keep a fixed size array and move them around.
I see, okay.
That's just practically, I mean, people have tried pretty much every which way. And so people have tried changing population size and this sort of thing. So, for example, to change the convergence rate and so on. Yeah. Okay. Right. Yeah, just not that one. That one. Right. Okay. So you can think of it with this sort of diagram. You can think of of us treating two things at the same time. So there's the genotype sort of goes around the top loop, and the phenotype goes on the bottom loop. The phenotype is, you can think of it, if you're used to reinforcement learning, as the environment. So that's where the phenotypes are everything that we calculate, you know, the creature's physical characteristics. That's why we calculate its fitness. The reason that this is an interesting and useful way to do things is that we're only operating on something at the top, which is just a discrete set of data. So it could be zeros and ones or something. Whereas this thing at the bottom can be quite complicated. Like where you calculate the environment can be very complicated. Now you calculate the fitness. And the useful thing is that you may already have something where you've done a lot of work to calculate the environment. So I'm thinking in particular, say you have a friend with some string theory where you have to put in some numbers and you get some string theory data out, and you would like to find the models which have got 3 generations or something. All of that is part of the environment. So I don't have to do anything for my friend, apart from, I just ask him, well, can you give me your program? Just with as a kind of as a subroutine where I put in some numbers, and all I want to do is get out the data, you know, how many generators or something, and I just invent my fitness function by what comes out of this subroutine. It's kind of an entire black box. I'd have to look inside that black box. I just have to operate on the genotypes I put in. So that's the advantage of it. It's very modular, the whole way it's set up. And you'll see when I get on to simulated annealing and quantum annealing, that's the big difference. So you'll see that when you're doing something like that, it's much more, you have to do much more work to try and put things into the system. However, here it's really just, it's very kind of third party. You just take your code and you operate on someone else's black box. Right, so there was there's some controversy about why they work, these things. And so when Holland introduced them, he introduced this idea that there's something called a schema. And so here, this particular example, I'm going to use this schema, which is 61 dash 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 62 dash dash. So what these numbers are some alleles in the genotype which are more important than other ones. So I can, in this particular case, 61 could be the first 2 digits of X, and 62 could be the first 2 digits of Y. And those ones are clearly much more important than the ones which are like the 8th decimal place or something. And so I can think of a schema which is basically these 4 digits. So digit 1, 2, and then digit 6, 7. It could be much more important than the other ones. And so this is what Holland called a schema. And the idea is that if an individual turns up in the population which has got that particular schema, it will be selected much more often. And before long, that schema will spread through the population so that a large number of in the population will have that particular set. So that's how the convergence is supposed to work. he argued that there's an initial growth of this schema, and when you're doing selection for breeding, you're pushing the system towards some convergence. But it's not, because this is the important thing, it's not sort of that you're going to get stuck at any, hopefully you wouldn't not get as stuck as if I was doing gradient descent, because there's the mutation going along as well. And so mutation will push you away from convergence. So for example, every so often, someone in this schema, with this schema, will get mutated, and maybe the 1 becomes a 0 or something, and possibly that's a much better schema. Once that appears, that schema will then take over and it will replace this one, start to replace this one. So there was controversy about whether that's really true, especially if you take into account that this is, the population may be 50 individuals or something. So any kind of probabilistic arguments are going to be slightly, just slightly affected by the fact the population is not normally that large. But anyway, it was rehabilitated a little bit. So the history of this is that there was a lot of papers by Polly. So if you want to know this particular part of the story, just look for, well, if you go to this review by White, an overview of schema theory, you'll see links back to these papers by Polly. So I think Polly kind of rehabilitated this idea a little bit. And then there was this work on the idea of fitness distance correlation, which also seems to be important. I have to say that if I look at the literature where people have tried to understand what's going on, it tends to be influenced quite a lot by what people assume about the genetic algorithm they're using. And so it depends a lot about the problem that they're looking at. And so, it's I think the literature is influenced quite a lot by that. Anyway, so the schema here, it would be this particular, say, 6-1, 6-2. That would, and you can see it's sort of operating because the individuals start to align along these particular rows and columns. So you see that these individuals here have got this particular schema, 6-1, 6-2. These ones, they just have the 6-1 part, and these ones only have the 6-2 part. And so you see at some point, maybe someone from this column bred with someone from this row and came up with this schema where they got the 6-1 from one of them and the 6-2 from the other one, and then off it goes and the schema spreads. So that's how it works, that's supposedly. So there's a formula that goes along with it, with this schema theorem, which I should just show you, which looks like that. So what it does is it tells you that if I'm at time t, and I go to time t plus 1, and I ask how many individuals in the population have got a certain schema, there's a formula that tells you the minimum number. So it's that the t plus 1 number in the population is greater than this. And if you look at this formula, this is the fitness of the individuals with schema S divided by the average fitness. And so you see that that's what is making an increase in the population. If I set the number to be, so when there's only one individual in the population, or maybe 2 or so on, and you work out a little differential equation, you'll see it's exponential. You'll get an exponential from that. The important point here is this bracket at the end. So the 1 minus PM. So PM is the mutation rate. And it's this bracket raised to the order. So the order is, in this case, it would be 4. So that's the number of alleles that are important. And you see that the larger the mutation rate, the worse this gets, because you're multiplying by something which is a number smaller than 1 raised to some power. So if my mutation rate is too high, it will slow down my growth. So basically, the more PM is, the larger PM is, the more I tend to spread out of a particular minimum or maximum in this particular case. Okay. Right, so that's the sort of the general story, is that selection pushes towards convergence, mutation pushes the system away from convergence. Yes.
Can I just confirm, with the genetic algorithm,
you choose the same splicing technique every time.
Yeah.
You would think that that would mean that, say, an individual had the good schema, then a load of junk data would be associated with the good schema,
Right.
and be propagated over time. And that might be solved by changing the way you splice. In practice, does that actually improve things?
So the issue of junk schema is actually an interesting one. I don't know if anyone's ever thought about that. Like, you mean like junk DNA, for example?
No, not in the same way as junk DNA.
Oh, okay.
I just mean that, like, say that the 6162, that's associated with one half of the splice, right?
Okay, right.
And let's say that one member of the population gets that 6162 bang on first time, and that the fitness is going to be very, very high for that individual. So they're going to breed successfully.
Yeah.
So the remaining half of the splice that the 6162 is contained in, that's going to be passed on very successfully as well. And only mutation is going to change those digits. That could be fixed maybe by changing the way you splice so that you get lots of different children,
right,
with those digits changing around. I don't know if I'm making sense. Yeah, so if you change the place you splice, oh, you do, right. Okay, that's what I would have thought.
Okay, right.
Yeah. Okay, thank you.
Yeah, so the splicing point is random.
Yeah. That answers my question. Thank you very much.
Okay, thanks. Oh, okay, but you can ask something. So now you have to ask something. Right, okay, so that's the setup of the whole thing. Are there any more questions before I talk about sort of various tweaks and optimizations and things to think about? Right. All right, so there are various things that you may do in order to optimize it. So I've mentioned some of them already, and let me just sort of list the ones that I can think of right now. So one of them is how you select, and also how you calculate fitness. And I find that the best sort of method is rank selection. And I'll tell you, well, I'll give you some explicit examples later, but I think it's the best way to avoid sort of degeneracy. So if my landscape is very flat, so maybe it has a tiny slope, but I still want to find where the minimum is. If I don't have something which is just rank selection, if I decide to calculate my fitness based on the height of the function, it's going to be very hard to distinguish individuals that are sitting in this flat direction, almost flat direction. And so actually for string theory, if you know string theory, that's a kind of very important point, because you do get a lot of flat directions. Also any kind of supersymmetric theories, you tend to get flat directions. So rank selection is a way to avoid it, because you see that if I have something, a very shallow valley, and I want to know where the minimum is, I know, and I have two individuals sitting on it, all I need to know is that this one is better than that one in order to be choosing that one more. So rank selection, I think, is I really recommend it. You try whatever you like, but I mean, rank selection is, for me, I think it seems to work as well as anything else. Something else which is useful to do is what's called elitist selection. So when I have a new population, I take the old one and I take the best individual from the old one, and I allow that one, I copy that one into the new population. And so typically what I will do is I will take the worst individual in the new population and put it against a wall and kill it. And I will replace it with the best one from the previous population. So it's a very brutal subject, obviously. Another way is, another thing people do is breeding. So you can try and avoid edge effects by having different crossover, more than one crossover point. One thing you have to avoid, though, is to have too many. It just becomes random selection, basically. It just comes out random. One important point is to optimize mutation rate. So mutation rate is a continuous parameter that we can vary. And that's the way that we can tell if the thing is actually working better than a random search. And so if I have a mutation, and I'll show you an example in a minute, I have the mutation rate is like 100%. It's basically a random search. So I just dial it down, and you should find that there's an optimum mutation rate. No mutation will also not work, though. So that's the point. So something else which is, I don't particularly find it useful, but it may be useful to you, is if you are doing something like where the parameters you're looking at are continuous. So for example, I'm interested in a parameter being 1, but my population is at 0.0999. So 0.0999 is about as far away from 1 as you can get in the Hamming space, you know, so in the codes, in the genotype, but it's clearly very close in the phenotype. So there's something called creep mutation, which is where you also do a mutation based on the phenotype. So you take the best individuals from the previous population, and you'll do a little mutation on those, and you'll copy those into the new population. So that was called creep mutation. So you'll sort of mutate the phenotypes, run genotypes. That I don't really like it because it goes against the whole ethos of the thing. But anyway, it exists in case it's something you might be interested in doing. Right, so now that's the layout. I'm going to now talk about a particular example and show you how it goes. So, any questions? Right, so let's look at this particular problem, and I'll show you how we can solve it. And in the tutorial, one of the problems will be to just to solve this. Oh, isn't it? Okay. Right, okay. Anyway, so this is the problem. So they're called taxicab numbers. And I thought I would treat this one in honor of Hardy, who was in the LMS. And so this is a taxicab number. It's the smallest number which I can write as the sum of 2 cubes in 2 different ways. So that's a taxicab number. So the definition is it's the smallest number, but I'm going to just extend it to be any number that I can write as the sum of 2 cubes in 2 different ways. And I can do it, I can think of more general numbers, and people do. And so I can think of can I write a set of numbers to the kth power, m numbers, and that sum is equal to n numbers raised to the kth power. So the number that is defined by that we call TKMN. K is the power, M is the number on one side of the equation, N is the number of numbers on the other side. So for example, 729 is the smallest T322 number. Pythagorean triples are T212 numbers. Right? So sum of a square is equal to the sum of 2 other squares. Fermat's last theorem is that there are no TK12 numbers when K is greater than 2. And if you have thought about anomalies ever, anomalies are really, if I'm looking at 2 theories that are the same and the same anomalies, those are T3MN numbers. You can kind of think of anomalies as just a sort of these numbers. Not quite, because of mixed anomalies, but generally you're thinking about cubic equations if you're doing anomalies. So there's a T3MN numbers. Right, okay, so let's just think about this problem. How can I find this number 1729? And so I'm going to encode that problem as a genetic algorithm. So what I'm going to do is I'm going to have 4 integers. I need 4 integers. And I'm going to take the cube of them. So the 4 integers, I'm going to generally refer to them as WI. I've got index I. And I'm going to binary encode these integers. So it's the sum of 2 to the L times by some binary number, TLI. So these TLIs are going to be my genotype. And so if I've got 4 numbers, my entire genotype is going to be just a row of 1s and 0s that look like that. So this is the first number, second number, third number, and so on, fourth number. So you see, it's actually a big search space because I've got 4 beta alleles. Beta is the size of the binary encoding, which I'm going to consider. So the search space is 2 to the 4 beta, which can be pretty big pretty quickly. Right, okay, so just for later, so when we get onto annealing, the way that you would solve this in annealing, and we will look at this problem with annealing, is I would take this binary, I would take this, for example, and treat it like a loss function, and I would try and minimize that. So this would then look a lot like an Ising model. You can reduce this to an Ising model. So that's the way that you would do this in annealing. Anyway, we're not doing annealing. We're doing genetic algorithms. So this is genetic algorithms. So now I need to take, if I have an individual, I need to figure out its fitness. And so the fitness I can write, so this is, I'm just now showing you chunks from my code. And so, actually, it's an aside, I had to write some code for this, and because I didn't have anything particularly suitable. So I went to ChatGPT and said, can you write me some Python code to solve taxi cab numbers? It was entirely useless almost. So I'm not yet threatened by ChatGPT, I have to say. At least not for lecturing this sort of thing. Anyway, so this is how I'm going to define my fitness. It's so what I'm going to do is I have to do lots of tests. So for example, I need to avoid in these integers that I have two integers the same on both sides of the equation, right? So obviously that's not right. And so if I find that W0 is equal to W1, also W0 equal to W1, I also don't want. I want 4 different numbers. So I just test that all the numbers are different. If they're not, then I just add a punishment. So I'm gonna add a penalty to the fitness. So this is my lam here. Lam is just a number. So I'm gonna add lambda. This has to be quite a large number because I have to compare it also later on. I'm gonna figure out a contribution coming from cubes. So it has to be something that can compete with cubes. So I have a large number I add to the negative fitness if things don't work. And also if any number is 0, I also give it a punishment. Because I mean, this is just me being lazy. I could just do my binary encoding so it doesn't include 0. But because I couldn't be bothered to do that, I just say, okay, well, I'm just going to punish it if it's 0 instead. And then I add something which is the actual condition that I want, which is the equations are the same on it. So it's the same on each side. And so it's an equality. So I've got W0 cubed, W1 cubed. I subtract those 2 numbers cubed, and then I take the absolute of that. That's how it's just like a loss function, essentially, that you can think of it as. So a solution to the problem we'll have f equals 0. So that will be f equals 0. Non-solutions are negative f. So this is negative f. So f is less than 0. And so what I do is I rank them in f. So I just look at all of my individuals and I just rank them in f. And so you can see the advantage of what's going on here, because all of this stuff that I'm doing here, this would be the same kind of operation. It's sort of irrelevant to how I get these W numbers and what they correspond to. I just have a module, I have a subroutine which just determines, do I like this individual or not, based on its phenotype and what's come out. So these W numbers could have just come out of anything. They could be generation numbers, or it doesn't really matter. But I don't really have to worry about where they come from. I just decide what a fitness is going to be for each individual. Right, so then what I do is, so I'm sorry for showing you my code in public. It's very rude, but anyway. So then I just arrange my population in an array. So I then reorder things depending on their fitness. So I just reorder them depending on their fitness. And then I select a breeding pair, which is based on the position in the array that they are in the population. So there's something I call likelihood, which is the probability of selection. And then all I do is I kind of roll the dice between 0 and 1, and I will select it if this number is less than that particular probability, and I don't if it's greater. Right? So, and if I do, I construct a breeding pair. I will, of course, do this n pop times to get n pop breeding pairs, and that's basically the way it goes. Right, so this is rank selection. It's also, I'll talk about selection types in a minute, but there's something people refer to as roulette wheel selection. This is a particular type of roulette wheel selection, let's say. So one other thing I'm just going to mention, is that the end of my coding? Yeah, so one other thing I'm just going to mention is to write a genetic algorithm is very quick. So it will take you maybe 200 lines or something, compared to something like if I'm doing reinforcement learning or neural network or something. It takes a lot more work to do that. So a genetic algorithm is something you can really do in an afternoon to write one. So it's very simple to code one. Right, so now let me just talk about the selection. So roulette wheel selection is this generic type where you base the probability, a likelihood of selection based on fitness. Rank selection is essentially the same thing, but the fitness is calculated from the rank. There's something called steady state, which is where, it's something I mentioned before, it's where you don't replace the entire population, so you don't have generations. I just replace a certain number of individuals every time I go around. So I'm just continually selecting breeding pairs and then selecting poor individuals in the population to go and replace them with the new ones. So that's called steady state. There's something called stochastic selection, which is similar to rank selection. And then there's other things that you may hear of. So tournament selection is where you compare a set number of individuals in order to select them for breeding. So you'll select individuals and then you'll do a kind of little tournament select and take the best few out of that. So that's tournament selection. And then there's a couple of other things. Truncation selection is kind of probably the least good. Truncation selection is where you basically only take the top, I don't know, 2/3 to breed and you ignore the bottom third. So that's the simplest thing, but it doesn't really work that well, so it's not the best. Right, so then there's mutation. So this is my mutation module function. And so what you do is you just go around mutating alleles at random, and what you will find is that if you plot the number of times number of calls I have to make, number of times I have to construct an individual to find the solution, and I plot it as a function of mutation rate, you should find some graph that looks like that. And I'll show you similar graphs later on for other problems, but you should find something like that. If the mutation rate is 0, it doesn't work very well. And if it is, if I go to something which is extremely large, it also clearly is just a random search. Right, so now let me show you it at work. So this is now the code with a taxi cab and the taxi cab number. Right, so this is just me running it. And so you see it finds one after, it tells you the number of calls at the bottom, but that was like, so 1100 for that. So you see it works pretty well. And I just show you, yeah, so this is the last, oh, okay, that's not the last one. So something you find, oh, okay, that's where it doesn't work. Okay, I'm just gonna pause this at some point. One thing you notice is that it's really not obvious when I'm just looking at the phenotype improvement, it's not obvious as it improves what's happened. You know, so your tendency is to look at so for example, the fitness -2 and think, oh, okay, it must be close to the fitness -1 individual somehow, but it's actually not. It's just that they're completely separate individuals in the population. They've just been coming in a new generation from breeding previous individuals. So despite the fact, you know, you're continuing to get better fitness, it's not obvious how it's happening. Not really obvious. See, these numbers, the actual numbers, so 5425, 17919, they're actually not really related at all. Okay, so this is the same thing if I put 90% mutation rate. And so you see, it just doesn't really converge very fast at all. It's just, it gets stuck essentially. So it gets stuck. It's not really doing anything. And the other thing you'll notice is it's stuck at, it's quite a large parameter space I'm looking at. So my beta is relatively large. And you see, it's kind of stuck in the outer regions of the parameter space. These numbers are huge. So it's not really focusing down to the smaller numbers, which is where you can find the solutions, you know, 1729. And so, you know, it really doesn't converge well at all. So let me say a little bit also about rank selection. So if I compare the different sorts of selection, So for example, truncation, tournament, stochastic, or fitness proportional. You see, it doesn't actually make that much difference. However, in the end, rank selection becomes important, and especially in physics sorts of problems. And the reason why is that you can get situations where your fitness is almost zero, but not quite. So it's, you know, it's kind of the flat valley problem. And so if I have something which is fitness -1, you see the two numbers, these, if I cube the 14 and 30 and I cube 23 and 26, they're only one different. So you see, this is you would call it a very fit individual, but is it 35 times fitter than that one? That one, it generates these two numbers, which they're 35 apart, so it doesn't look very good. But then these numbers are kind of close to 13832, which is a taxi cab number. So it's not obvious how you should do the fitness if I don't choose rank selection. A rank selection is really something which I recommend. Okay, so how am I doing for time? We've got 20 minutes or something. So I just want to talk about, I'm going to finish by talking about the possibility of combining genetic algorithms with other methods, because actually I think this is something people could try more. So I haven't seen it done that often in the literature, at least not in this kind of physics-oriented genetic algorithm literature. So I'm going to show you what I mean by combining genetic algorithms with, and it's, you see, in these particular problems that we look at, is something that you may want to do. So what we've seen so far, genetic algorithms are good at exploring parameters with very complicated problems. Their convergence rate is initially very fast. So initially they will cluster around all of the possible solutions very fast. But what you find is that the convergence rate, the final convergence rate, is very slow. And so that's partly because we put in the mutation in order to get it to explore all of the parameter space, but the penalty we pay is that when it's getting around a solution, it doesn't really converge. It just sort of fluctuates around. It just fluctuates around the solution. So one way around it is to dial down mutation. And so, you know, when after a few generations, this is something people try. After a few generations, you're all clustered. You dial down the mutation rate in the hope that you will start to converge closer and closer to the solution. However, if I'm, for example, my original problem, if I want to do 250 decimal places, it's going to take me forever in order to converge. Right? So I'll just never get there. However, I know that once I'm at that point, once I'm close by, I could just do something like gradient descent to find the answer. Right? So depending on the problem, I could just find the answer. So that's really, I think that combining genetic algorithms for the beginning and then doing something else is something which I think is more useful than, it should be tried more often than it is. So I'll show you an example. And so the thing we came up with, it was in this paper with, so Fernando Quevedo, amongst other people. What we recommended was you should begin with a genetic algorithm. Right? So you're exploring the whole parameter space. Once you've clustered, you then do a clustering algorithm to choose sets of clusters. From those clusters, you then do what's called a Nelder-Mead, which is a bit like a gradient descent, but when the problem can also be discrete. And so if you do that, you'll just find that you can solve things far more quickly than any of these things individually. So I'll just show you what happens in the particular examples we looked at. So these are kind of, this is kind of in the context of string theory. So there were KKLT-like models. And if I look at those, the potential is quite often looks like this. So it's very flat, you see, and there's a minimum there, but I would have trouble finding the genetic algorithm. So that was the context. So now let me just show you something a bit easier to show you, which is our famous potential. This potential that I started with. So the question is, is there a better way to find the maxima or minima of this function? So I turn the function upside down so I can call it minima. So this is my potential. So what we do is we start off doing a genetic algorithm. So the genetic algorithm, it focuses like we saw at the beginning. So we end up with after a few generations, just 10 generations, we end up with everyone is clustering around it's a local minima, around local minima. And then what we do is so that's our initial convergence. And what we do is that we then take the population and we divide it into these clusters. And from each of the clusters, we make a simplex. So a simplex is just if the dimensionality is D, the simplex is D plus 1 individuals in the dimensions. And so in the two-dimensional problem, I choose 3 of the individuals from a cluster. So I'll take the best 3 in the cluster, in each cluster. And then I'll do this. So there's a k-means clustering algorithm that I can use to do that. And then I'll do this procedure, which is Nelder-Mead, it's called. So the Nelder-Mead method is a kind of gradient descent. So what I do is I take the worst individual in my simplex of 3, in this case, and I reflect it around the next 2 individuals, so around the other 2 individuals. I reflect it well, in principle, it's in some code space. In this particular example, it's kind of obvious because it's just 2 dimensional. So I just reflect it around these 2 individuals. So I kind of walk down into the minimum that way. And you repeat it several times, and it doesn't really take many Nelder-Mead steps to find the minimum. In this particular case, maybe 4 or 5 or something. You get very close to each minimum. So if I then repeat this several times, I end up with basically every single local minimum. And then if I want to know what the lowest is, I will just compare the whatever 10 of them or something. But that's the way it works. You'll find every local minimum in the problem. And it doesn't have to be a continuous problem. It can be these could be discrete. It doesn't have to be continuous. So it's something I think should be looked at a bit more closely. Okay, I probably don't have time to talk about that. I was going to discuss probing continuous parameter spaces, which I think kind of by now you can imagine how it would go. So this is a particular example we were looking at, which is doing some sort of like a phenomenological search with a supersymmetric model with a lot of parameters. So I'll just show you this one thing, which you should see, which is that. If I have something with 19 continuous parameters, and I show you a slice through parameter space, and I say that everything falls within this ball, and the parameter space is actually the cube, the ball is only 10 to the minus 7 of the volume of the cube in 19 parameter spaces. So if you're ever at a talk and someone shows you a scan which is covering what looks like most of the parameter space, like that, they're probably lying to you if they have more than, say, 4 parameters that they're looking at. Right, okay, so I'm going to close there. So let me just sort of summarize everything. So genetic algorithm, it's one of the most effective meta-heuristic search methods. And compared to what I'll show you tomorrow, the things I'll show you tomorrow, they're more direct construction of the problem in, for example, an Ising model or something. Whereas this is really a kind of black box you can look at in any system that you want to optimize. So they excel at problems where the search spaces are very difficult and there are local minima or maxima, local optima, and you want to find out which is the best solution and possibly find out which are, a whole load of equally good solutions. You can do it that way. They're constructed with these 3 components, so selection, breeding, mutation. They have this particular property that they will quickly converge, but the final convergence slows down. So what they do is they tell you very quickly where the good points are in the parameter space, and you can optionally try and find some other means at that point to try and find a local optimum point. And so I think they probably still have sort of potential that they could be used in that way. So now let me talk about the tutorial problem a bit. So this afternoon I'll be a tutorial with Thomas. So you'll have 2 problems. Oh yeah, you're right. The taxicab problem's not there. That's tomorrow. You'll look at taxicab problems. So today there's minimizing a continuous function with a genetic algorithm, and also knapsack problem if you get onto that. I don't know if an hour is really long enough to be getting onto that. Anyway, so please have a look at the and be able to run a Jupyter notebook. So the example you'll need to run is in that Jupyter notebook. Okay, thanks a lot.
Sorry. So you know how you said there's like a probability of different members of the population breeding?
Yeah.
How does that link to, because you're not just breeding one thing, you're breeding them together. So how do you sort of match them up? Makes sense. Like how do you, like if one thing has a percentage chance of 0.9, like how does that match with something else that's a percentage of like 0.7?
I didn't get the.
So how do you basically match up your breeding pairs in your population?
Okay. I mean, they're really just done. It's really a random selection with the additional probability of selection from the fitness in the population. So I'll select one to make a pair, and then I'll select another to make a pair with that probability, and then I'll put them together. Yeah, like in life.
Is there any work in genetic algorithms on constraint optimization other than just sort of building it into the fitness function? Is there something you can do to the algorithm itself?
Yeah, so that is a good question. I don't think there's a very good way to put that into the algorithm, actually. The only way to do it, I think the only way to do it really is to design your genotype so it's already satisfying the constraints. So, I mean, I think there will be a way to do it. If, for example, I have something, so there's a parameter space, everyone has to live on a sphere, for example, so that I would have it that my genotype is constructed so that the sum of its projected genotype, so it's invariant under genotype goes to genotype times lambda or something. I could imagine doing something like that.
Hi. So in nature, we also have asexual reproduction.
Right.
This is the first I've seen of genetic algorithms, so I'm not sure why the mixing of genetic information is so important in particular. You might imagine that if you just take one individual and kind of split it into several different nearby individuals, that might also work. Right. Has that been tested, and is there an advantage in particular of the sexual nature of this?
Right. So I think the breed is important. If you, for example, so say in the 6'1", 6'2" example, and if one individual's got 6'1" and the other has 6'2", I need to make an individual which has got both. So I then need to be lucky and get the split in between the 6'1", 6'2", and then get a child from that. So I think that's why the breeding is important. Yeah, that's how to make new, better schema from the older ones. The mutation is important. One thing that it does, which I didn't stress enough maybe, is that you can have a situation, if a schema is very good and it just goes through the entire population, you could have a situation where one of the alleles, they're all 0, for example, and then I can never make a 1 there because unless I have a mutation, I can't make the 1. So it becomes a kind of sterile thing because you'll get like alleles where everyone is just like the same. Yeah. So there's those two aspects.
Thanks.
Hi. Is it ever favorable to change the mutation rate during the search, perhaps as you approach convergence to reduce the mutation rates?
Right. Yeah. So that's one thing that people do try, is that if I want to find a better solution, if I want to zoom in on a solution, that you could maybe improve the mutation rate, dial it down in order so that people focus better. I think what works probably better, maybe in conjunction with it, is that if I'm say looking at that particular example between 0 and 10, and then I say, okay, well, I have a cluster here, which is around 6'1", 6'2", or something. I'm now going to look at the smaller parameter space, And so then I map everything, I map the entire population down into this parameter space, which is between, say, 6 and 6.3. And then I'll look at that box. And that is probably a better way to converge than just mutation.
Thank you.
So if I want to optimize a continuous function, and so I have a wide array of methods at my disposal, including ones that take like derivative information into account, can you make any comments about when I would expect, like in what particular situations I would expect genetic algorithms to outperform the like many other methods that I would potentially use?
Yeah. So I think where they do better is if I have something with a lot of local minimum. Yeah. And so that landscape, even though it's kind of toy landscape, it's a typical sort of landscape where a genetic algorithm would perform better than other things. Where it doesn't do well is then, the final convergence. So that's why I think I didn't really get time to talk about it. But if I'm doing like a scanner parameter space with continuous parameters, and I may have, 4 or 5 different solutions, one way to operate would be just that we'll take your genetic algorithm, you find a cluster, find a set of clusters, and then you'll look around that solution and you'll sort of zoom in on that, and then you'll maybe do Nelda-Mead, or you could just do a more focused genetic algorithm around there. Yeah, so I think that's where they would be better. I mean, in principle, when you have a simple problem, it's kind of what people do anyway, because you'll do like an initial random scan and you'll see, okay, this looks an interesting point, and then they'll focus in on that. So it's kind of what people are doing, but it's a way to just automate it so that you'll just do it immediately, and then you'll see where the interesting points are.
Thank you.
I wanted to ask, are there any precise statements in terms of what kind of problems or what kind of conditions should the optimization problem satisfy in order for GAs to be applicable?
There's very few precise. Yeah.
I expect the expectation is that if you try it on all optimization problems, it will fail on the majority.
So that question is probably undecidable. I don't know of anything where people have said, it will definitely not work on that particular problem.
Any other questions? Let's thank Steve for this wonderful